All right, in this video, we'll talk about solutions to homework problems from section 8.2. Section 8.2 is on series, where we have taken our idea of sequences, and we now know that if we add the terms of a sequence together, we get a series. And so we're going to work on some of the homework problems from section 8.2. Now, if we start with something like question 5, the instructions in question 5 say find at least 10 partial sums of the series, graph both the sequence of terms and the sequence of partial sums on the same screen. So we won't be doing that, obviously, because that involves our calculator. And then it says, does it appear that the series is convergent or divergent? If it's convergent, find the sum. If it's divergent, explain why. And so question 5 starts with the sum n equals 1 to infinity of n divided by the square root of n squared plus 4. Okay, so that's our series. And they want us to find at least 10 partial sums. Now, I'm not going to find 10 partial sums here, but we can find a few. S sub 1. That's what we get by plugging in 1. So we would get 1 over 1 squared plus 4. So we would have 1 over the square root of 5. S sub 2 would be what we get by plugging in n is 1 and n is 2. So we would have 1 plus the square root of 5. That's our first term. Remember, when we get this, this will be a sub 1 plus a sub 2 plus a sub 3. Our series looks like this. Our first partial sum is just a sub 1. Our second partial sum is a sub 1 plus a sub 2. So we have to find a sub 2. So we get a 2 here. Here we would get a 2. 2 squared is 4. So we would have plus, and we would have 2 over the square root of 8. 2 squared is 4, 4 plus 4 is 8. Now we can simplify that. That's 1 over the square root of 5 plus, and now 2 over the square root of 8, root 8 is 2 root 2. So that's 1 over the square root of 2 when we simplify that. S sub 3 then would be a sub 1 plus a sub 2 plus a sub 3. So we would have 1 over root 5 plus 1 over root 3 plus, sorry, that's 1 over root 2, isn't it? I apologize for that. Plus we get by plugging in 3. So that would be 3 divided by 3 squared is 9. 9 plus 4 is 13. So we would have the root of 13 here. And of course, we would use our calculator to work these out, right? We'd use our calculator to work them out. S sub 4, we'll go ahead and do S sub 4. That would be 1 over root 5 plus 1 over root 2 plus 3 over root 13. That's the first 3 terms plus the 4th term, which would be 4. 4 squared is 16, right? 16 plus 4, this would be root 20. And of course, we could simplify that. Root 20 is 2 root 5. So if we did that, root 20 is 2 root 5. So we'd have 2 root 5 down here. The 2 would cancel the 4, and we would have 2 over root 5. If we do just S sub 5, and we'll stop there, we would have these terms here, right? This one would go here, and this one would go here, and this one would go here, and this one would go here. Plus, when we plug in 5, we would have 5. And on the bottom, we have 25 plus 4, and we'd have the square root of 29. Now, that doesn't simplify any more than 3 over the root of 13 simplifies. So we would just add all those together. So the first part of this problem is just to add them up. And then they ask us, does this appear to be convergent or divergent, right? Does it appear to be convergent or divergent? Well, what is he doing to us here? He wants us to make some kind of a conclusion. He wants us to get a decimal here and a decimal here and a decimal here, and then get a decimal here and a decimal here, and take a look at these and ask ourselves, wow, are these growing without bound, or are they getting bigger, but bigger with a limit, and thus they're going to converge. This series is going to converge. And what he's trying to illustrate for us here is that our intuition is not the best way to go about this, right? And that's why in the instructions, he then goes on to say, does it appear that the series is convergent or divergent? If it's convergent, find the sum. If it's divergent, explain why. Now, we have our test for divergence, right? And our test for divergence says if the limit, right, if the limit of our general term is not zero, then this series diverges. So if we're going to take the test, we would do the limit as n goes to infinity of our general term, which would be n divided by the square root of n squared plus 4. Now, we were taught in Calc 1 how to evaluate this limit. N is going to infinity, so it's positive. And so we would rewrite this as the limit as n approaches infinity. In the denominator, we would have n squared plus 4. We would divide by the highest power of n in the denominator, which is n squared. Here, we would then have to come up here and divide by the same power of n. Here we have n squared, but it's under a radical. So we would be evaluating the square root of n squared, which equals, remember, not n, it equals the absolute value of n. However, n is going to infinity, so n is positive. Now, in the case that this number is positive, then and only then does the square root of n squared equal n. And ours is positive. So we could rewrite this as an n, and we're left with this limit here. The limit as n approaches infinity of 1, n divided by n. This is going to be the square root. N squared divided by n squared is 1, and this is 4 over n squared. Now, when we evaluate that limit, this goes to 0, and we end up with 1, which is not 0. Therefore, by our test for divergence, since the limit of the general term is not 0, we know this series diverges. All right, so that's how we do number 5. Sure, you noticed since number 5 just disappeared that I paused the video. I'm going to pause the video to erase during this video just because I want to try to get a lot of problems done, and I don't want to have a lot of time wasted just on the erasing of questions. So the next question we'll take care of or take a look at is problem 12, and in the instructions for these problems, it says determine whether the geometric series is convergent or divergent. If it's convergent, find its sum. So they've told us that this is geometric. Now, given it's geometric, we want to find a, that's our first term. So in this case, that's going to be 4. And we want to find r. Now, r is our common ratio. So we have to ask ourselves, what did I multiply 4 by to turn it into a 3? What did I multiply 3 by to turn it into a 9/4? So what did I take 4 and multiply it by to turn it into a 3, right? Well, if we solve this, we see r equals 3 over 4. And then we can ask ourselves, is that really true? If I take 3/4 and multiply it by 3, Yeah, I get 9/4. If I take 9/4 and multiply it by 3/4, 3 times 9 is 27, 4 times 4 is 16. So R is 3/4. Now, we were given some theorems about geometric series, and we were told that a geometric series is convergent if, right, it converges if the absolute value of R is less than 1, i.e., if -1 is less than R is less than 1. If R is between -1 and 1, which ours is, this converges. So this series converges because the absolute value of R is less than 1. And then they wanted us to find the sum, right? The sum. And we have a formula that says the sum is A over 1 minus R. A here for us is 4. R is 3/4. And so if we do our arithmetic here, we have 4 divided by 1/4, 1 minus 3/4, and that equals 16. So it sums to 16. So that's how we do problem 12. Problem 16, again, remember, we're given that this is geometric. They've written this as a series, n equals 1 to infinity, and we have 10 to the n divided by -9 to the n minus 1. And if we write down a few terms of this, right, if we put in n is 1, we get 10. And if we put n is 1 down here, we get 1 minus 1 is 0, -9 to the 0 is 1. If we put in n is 2, we get 10 squared. Down here, we get -9 to the 2 minus 1. That's -9 to the first, so we would get -9. If we put in 3, we get 10 cubed. If we put 3 down here, we get -9 squared. -9 squared is going to be positive 81. And now we can set about to try to find A and try to find R, because again, remember, we were told it's geometric. So here A equals, A is our first term, so A is 10. R is going to be what we multiplied this by to get this, right? So what did we multiply the first term by to get the second term? Well, we multiplied the numerator by 10 because the power went from 10 to the first, 10 to the second. Here, 10 to the second, 10 to the third. And then the denominator looks like we took 1 times -9. So we multiplied this by -9. Now we're going to check that over here. If I multiply this by 10, I get 10 cubed. If I multiply this by -9, I get positive 81. So this is my value for A and my value for R. Note, however, here, the absolute value of R equals 10/9, which is greater than 1. Therefore, this series diverges. We don't use our formula here to find the sum because it does not have a sum. It's divergent. If we were not aware that it was divergent and we just plugged our numbers in up here, we would get an answer. It'd be wrong, but a number would come out of that. If we just plugged this in, right, we would have A is 10, that would go there. We'd have 1 minus 10/9, that would go here. Of course, 1 is 9/9. And so we would have 10 divided by -1/9, and we would get -90. Now, that's wrong. The formula doesn't know the series diverges. We have to decide the series diverges. And because we decided using our value of R being the case that the absolute value of R was bigger than 1, therefore it was divergent, we knew not to do this step, right? We would not have done this step because if we did this step, the number we're going to get is not the sum. It's just a number from a formula that should have never been applied in the first place. All right, next we'll look at number 27. 27 is for the sum n equals 1 to infinity of arctan or inverse tangent of n. Now here, having a little knowledge about the graph of inverse tangent pays off. We know the graph of inverse tangent behaves like this. It has a horizontal asymptote as n goes to infinity of pi over 2. And therefore, we can look at our test for divergence, right? We can do that. We can take the limit as n goes to infinity of inverse tangent of n. We know that that limit is equal to pi over 2 because of the graph of the inverse tangent function. And that's not 0. Therefore, this series diverges by the test for divergence. We want to state why it converges or why it diverges in our conclusions. All right, so let's take another problem here. We'll look at 28. See if we can fit that one down here so we don't have to pause the video before we're done. 28, oh yeah, I think we can fit this one here. So here we have the sum, n equals 1 to infinity of 0.8 to the n minus 1 minus 0.3 to the n. Now we can use our rules for series and we can write this as two series. This is n equals 1 to infinity of 0.8 to the n minus 1 minus the series n equals 1 to infinity of 0.3 to the n. And we can look at each of these series individually and see if they converge or diverge. If we were to write down a few terms of this, right, when n is 1, we get 1. 1 minus 1 is 1 is 0, and 0.8 to the 0 is 1. Here, if n is 2, we get 0.8. If n is 3, right, 3, we get 0.8 squared. So this series is geometric. And what do we know? We know A is 1, and we know R equals 0.8. How do we know that? Well, 1 times 0.8 got us to here. 0.8 times 0.8 got us to here. So this series, geometric, and it's convergent, right? It's convergent because R is less than 1. What about over here, right? If we add this one on, or I'm sorry, we're subtracting this one, aren't we? Minus. If we put n as 1 here, we get 0.3, don't we? If we put n as 2, we would get 0.3 squared. If we put n is 3, we would get 0.3 cubed. Also geometric, isn't it? A here is 0.3, and again here R equals 0.3 times 0.3 gets us 0.3 squared. 0.3 squared times 0.3, so this is 0.3, also convergent. Now by theorem, we know the sum of this series is equal to A over 1 minus R. The sum of this series is equal to A over 1 minus R. Here we get 1 divided by 0.2, which is 5. And here we get 0.3 divided by 0.7, which is 3/7. Now, by theorem, since these are each convergent, we know that the sum of this is convergent, or the difference of this is convergent. And we know that it converges to the difference between these two numbers, 5 minus 3/7, or 35/7 minus 3/7, which gets us 32/7. So unless I've done some crazy arithmetic wrong someplace, the answer to 28 is 32/7. All right. Next, we'll take a look at problem number 33. Now, the instructions on 31 through 34 says determine whether the series is convergent or divergent by expressing S sub n as a telescoping sum, as in example 6. So in other words, we're going to use partial sums here, right? So we have sigma, the sum n equals 2, I'm sorry, we're doing 33, n equals 1 to infinity, and we have 3 divided by n times n plus 3. Now, I'm not going to go through the work of doing the partial sums. We've already covered partial sums in this class. So I have already done the work for the partial sums, to be honest with you. And so this equals, once you do the partial sum calculation, the series n equals 1 to infinity of 1 over n minus 1 over n plus 3. Now, they want us to find S sub n, right? That's what they said. Express S sub n. So when we put S sub n in here, we're going to put n is 1. And so we're going to get 1, right? 1 over 1 is 1 minus 1 over 4. Now, they've told us this is telescoping, which means these terms are going to eventually cancel each other out. So we just have to keep writing like we did in our notes when we looked at the telescoping series in class, or if you've read example 6, which we covered in class. So when we put it in as 2, we get 1/2. Notice that doesn't cancel any of these. We put n is 2 in here, and we get 1/5. So we have to keep going to get an idea of how this is telescoping. Put a 3 in here, we get 1/3. Put a 3 in here, we get 1/6. Now, when we put a 4 in here, we're going to get 1/4 minus 1/7. And so finally, we got something that canceled. When we put a 5 in here, we're going to get 1/5 minus 1/8. When we put a 6 in here, we're going to get 1/6 minus 1/9. And if we put a k in here, right, just to see how this is going, if we put a k in here, or an n, it could be either one. If we put, I've written an n, so we'll do an n. When we put n in here, we get n over n, right? So what is this going to look like as we keep going? Well, we need to change this to a k, because we can't use an n because we have an n here, and we'd have n over n and n plus 3. So when we put a k in here, what are we going to get? We're going to get 1 over k minus 1 over k plus 3, right? That's what we're going to get for our kth term. What are the terms? Well, let's take a look at this now. What cancels here? This cancels with this, right? And then the 1/5 cancels with this. and then the 1/6 cancels here. So here we plug in a 1, here we plug in a 2, here we plug in a 3, here we plug in a 4, here we plug in a 5, here we plug in a 6. Now, if we plugged in a 7, we would have 1/7, that would cancel this. If we plugged in an 8, we would have 1/8, that would cancel this. If we plug in 9, we'd have 1/9, that would cancel this. So all the terms going forward are going to cancel. Everybody's going to cancel. We're going to have a 1 left, right? We're going to have a 1 left. We're going to have a half left. And we're going to have a 1/3 left right there. So everybody after the third term cancels. They all cancel. So when we take a look at this, what's bothering me is this is our last term, right? We put k here, we put k here, and we get this. But when we take a look at how this series is behaving, right? No one's going to cancel the k plus 3. Because to cancel the k plus 3, we would have to put k plus 3 here. We would have to go 3 terms, right? To cancel the second term here, we had to go 1, 2, 3 terms later. To cancel the second term here, we had to go 1, 2, 3 terms later. So to cancel the second term here, we would have to go 1, 2, 3 terms later, but we're only going to k. So there are no more terms. So this term is not going to cancel, right? That k plus minus 1 over k plus 3, that's going to be permanent. But that term is really right here. Because we had to go 3 terms later to write down the term that was going to cancel the 1 over k. So this is our kth term. So we actually have to back up here. We have to go to our k minus first term. Now our k minus 1, right? This is our k minus first. That's going to be 1 over k minus 1 minus 1 over, and this is going to be k minus 1 plus 3. That's going to be k plus 2. Here, we're going to have our k minus 2 term. So that's going to give us 1 over k minus 2 minus, and then k minus 2 plus 3 is 1 over k minus 1. K minus 2 plus 3 is 1 over k plus 1. And then here, we're going to have our k minus 3. Now that's going to be 1 over k minus 3 minus 1 over k minus 3 plus 3 is k. And that's going to be the term that cancels this one. This term here is also going to be canceled by the term that came right before this one. And this term here is going to be canceled right before the one that came here. And this one's going to be canceled by the one that came before. So we're going to be left with minus this, and minus this. This is going to be our s sub k. And then we're going to take the limit of this as k approaches infinity. And when we take the limit of this as k goes to infinity, that's infinity plus 3, infinity plus 2, and those are each 0. So we're going to get 1 plus 1/2 plus 1/3 minus 0, minus 0, minus 0. Or here we're going to get 6. That's 6/6. That's 3/6. That's 2/6. So that's going to be 11 over 6. So our sum for problem 33 is 11/6. So that was really tricky. We had to think backwards here to figure out, does that disappear? Yes, it does, 3 terms prior. Does that disappear? Yes, it does, 3 terms prior. Does that disappear? Yes, it does, 3 terms prior. Does this disappear? Yes, it does, 3 terms prior. And therefore, at the end, we still had some values left in our telescoping series that we had to write out. So that's problem 33. Next, we'll take a look at problem 41. And in problem 41, it says, find the value of x for which the series converges. Find the sum of the series for those values of x. So here we have the series n equals 1 to infinity of x to the n over 3 to the n, which is just the series n equals 1 to infinity of x over 3 to the n. And if we write this out, we get x over 3. And then we get x over 3 squared, and then x over 3 cubed, etc. And so this is geometric, because if you look at it, we go from this term to this term and this term to this term. Now, a is x over 3, and r here is equal to, well, we go from x over 3 to the first x over 3 squared, from x over 3 squared, x over 3 cubed. So r is x over 3. Now, remember, to converge, the absolute value of r has to be less than 1, i.e. the absolute value of x over 3 has to be less than 1. Now, if you're not really great at absolute values, that means -1 has to be less than x over 3, which has to be less than +1. We can multiply everybody by 3, and that will get us -3 has to be less than x, has to be less than 3. Therefore, we would be able to say the absolute value of x has to be less than 3 for us to converge. So this will converge when the absolute value of x is less than 3, i.e. when x is between -3 and 3. Then it says if it does converge, well, not if it does, because we were supposed to find the values that cause it to converge, find the sum. So remember, s is equal to a over 1 minus r. So that's going to be x over 3 divided by 1 minus x over 3. We can multiply the top and the bottom by 3, and we get x over 3 minus x as our sum. So that's how we do number 41. I'll erase this, and then I'll work on 47 as our last problem. All right, my last problem will be problem 47. In problem 47, they say that the nth partial sum of a series. So we have a series we don't know anything about. It's n equals 1 to infinity of a sub n. And we know from there, they've given us that the nth partial sum is n minus 1 over n plus 1. And they want us to find a sub n. They want us to find the general term. Now, what do we know about partial sums? We know that if we take a look at what a partial sum looks like, this is S1, this is S sub 2, this is S sub 3, this is S sub n, right? That's S sub n. Now, oh, sorry. That's S sub n. Now, that's the first place A sub n shows up in our list of partial sums. But so we need to solve for this. In other words, we need to come up with a way to make all of these disappear, so the only thing left is A sub n. Well, if we think about it, the term before this one is A sub 1 plus A sub 2 plus A sub 3, and it stops at A sub n minus 1, which, remember, is right there. It's the term before A sub n. So if I take S sub n from here and I subtract S sub n minus 1, when I do that, right, that's going to put a minus there, a minus, a minus, a minus, a minus. So these will cancel, these will cancel, these will cancel, these will cancel, and the only thing left is A sub n. So to find A sub n, I'm going to use the equation A sub n is equal to S sub n minus S sub n minus 1. The partial sum, if we wanted to find A sub 2, we would find it by taking S sub 2 minus S sub 1. S sub 2 minus S sub 1 would cancel these, and we'd have A sub 2. So A sub 2 is equal to S sub 2 minus S sub 1. A sub 3 is equal to S sub 3 minus S sub 2. So by the extension of that, A sub n is S sub n minus S sub n minus 1. Now we know what S sub n is. S sub n is found right here. So that's n minus 1 over n plus 1. And we know what S n minus 1 is. We're just going to put an n minus 1 here and an n minus 1 here. So we're going to have n minus 1 divided by n minus 1 plus 1. We put our n minus 1 right in here for our n's. Now we're going to do some algebra here, right? This is going to be n minus 1 over n plus 1 minus. This is n minus 1 minus 1. That's n minus 2. N minus 1 plus 1 is n. So we need a common denominator now, right? So our common denominator is going to be n times n plus 1. Now we're back in algebra 1. So here we're going to get n plus 1 into n times n plus 1, leaving us an n. Don't forget that minus sign now. Here we have an n goes into here. That leaves us an n plus 1 to multiply by this n, pardon me, minus 2. And what do we get now? I don't know. Let's see. We get n squared minus n, distributing there, minus, this times this is going to be n squared. We're going to have plus 1, take away 2. So that's going to be minus n. And then we're going to have 1 times negative 2. That's going to be negative 2. And on the bottom, we have n times n plus 1. So what does that get us? Well, these n squareds are going to cancel. We're going to have minus 2n plus 2 over n times n plus 1. I'm sorry, my phone's ringing. Give me just a second here to go pause that. All right, so, oh, well, there's an algebra mistake right here. This is minus n, and that's minus n minus n. These go away, and so these cancel, right? Because that's a negative n, 2 negatives make a positive. So we just get negative 2 over n times n plus 1. Well, I'm glad my phone rang then. So that's our general term. And then it says in the instructions, find the actual sum. So if we want to look for the actual sum, we have the sum, n equals 1 to infinity, and we have n minus 1 over n plus 1, right? So that's what we want to find, because that's our a sub, no, that's not our a sub n, I apologize. Our a sub n, I was distracted by the phone ringing and I haven't recovered yet, have I? This is n plus 1. This is what we want to find. We want to find that. And we know to find that, that's going to be equal to the limit as n goes to infinity of our nth partial sum of s sub n. And they told us s sub n was equal to n minus 1 over n plus 1. And we know from Calc 1 that we divide everybody by the highest power of n. That would be 1, that would be 1 over n, that would be 1, that would be 1 over n. So we would have 1 divided by 1, so our sum would be 1. All right. That'll complete our video for section 8.2.